So what I'm trying to understand is we have these various different ways to try to limit to the ruliad. Okay. And let me show you an example. Okay, so these are, it's basically a question of how do you add in new rules and what is preserved when you do that, and how does the state, I mean, we've got three different kinds of structures. We've got state structures, we've got token structures, and we've got causal structures. Am I making sense?
Mm-hmm.
Yes.
Okay, so let's look at what happens. This is a very simple rule, just 0 goes to 1, 1 goes to 0. Okay, but now we can also consider the tuples, the two-level rule for the same thing. So I'm saying the rule that has that includes more rules here, right? Do you get what I'm saying? Xerxes, do you understand what I'm saying? James, do you understand what I'm saying?
Yes, I do.
Okay, so that then produces a different structure here, right? For states, yes?
Mm.
And we keep going, and we've got these things that are not complete graphs, yet they would be complete graphs if the size of the rewrites gets as big as the initial state.
Right.
Right?
Yeah.
But they're not complete graphs yet. Their transitive closure would be a complete graph, but they themselves are not complete graphs.
Mm-hmm. Yeah.
Okay?
Mm-hmm.
All right. So now we can ask, what are the causal graphs associated with these? And I don't really understand yet how to think about the derivation of these. Okay, what really are these? This is asking, I mean, and I think that might be revealed by looking at the token event graphs. Okay, so then we can consider the same thing for our models here.
Yes.
And this is now looking at all possible rules of the form pair goes to pair. Okay.
Okay. Mm-hmm. Yeah.
So it produces this structure, which is not particularly symmetrical. The reason it's not symmetrical is that things have been canonicalized.
Mm-hmm.
That is, the states have been canonicalized. Okay. We can ask about the causal graph here, and we see various things like this, which I don't really understand very well. Okay.
Okay.
So our objective here is to understand how does this, I mean, we've got these different ways to do limits. And we've also got your approach, Xerxes, of doing completions as a way to get to limits, right? Yeah. So in other words, there's a way, this is just adding in rules for fun, so to speak. Mm-hmm. Your approach is to add in rules when you need them to complete a something, okay?
Yeah.
Right, so now, well, maybe we should look.
Each of these approaches of adding rules, and there are many, will lead to its own kind of, will reveal its own causal section, so to say.
Well, let's discuss what that means.
Okay.
Okay, so your claim is, okay, so in a sense, okay, so how do we think about the kind of, is it some kind of foliation type thing? And what does it mean? Okay, explain that statement, Xerxes.
Okay, so when one is just working with a simple multi-way system, you can follow some some collection of rules, and that gives you a causal structure. When you have multiple possibilities, you have multiple choices of how you want to follow the rules, and that defines its own causal structure. Now here, unlike the usual multi-way business, what you're doing is you're choosing, because you want to go to this limiting object, and of course there are many ways that you can go. Every choice that you make of going to this limiting object by putting rules in some way, you're just taking some random choice. In my paper, I took some particular other choice. Each choice will have within it by definition, it'll have some kind of causal sequence that one is following. So if you climb some set of rules and just pause there and try to look at the structure, you will get some information about what causal sequences have resulted as a result of those that choice of rule application. But of course, if you proceed with the next kind of parallel set of rules, then you'll start losing this information. In the end, the limiting structure is probably just one unique thing where everything is complete, and then you might be able to apply nothing further. But by the time you reach a limiting structure, you've mixed up all the possible causal information. It's not that it's not there, but you won't see it because it's all mixed up. You don't have a way to separate, you don't have a way to distinguish all the various causal structures that are just there all together once you reach the final limit.
Well, so, okay, basically what you're saying is, in limit, all possible causal structures are tangled together. And that is analogous. I mean, compare that to the multi-way causal graph, which has multiple causal structures.
Right, but at least in the multi-way causal graph, even though there are multiple structures, they are not tangled in the sense that you can still follow pathways, separate branches, and you can actually you can kind of take sections of it and obtain that information.
No, but you can do the same thing here. I mean, all I have to do, I had some nice pictures here.
You can do if you have the information of how you climbed up that ladder.
I understand,
but if you're only looking at the end result, you don't know how you climbed up that ladder.
I understand, but it's the same thing it's the same statement. Okay, you're saying, okay, so there are pictures here of, those are particular rules, right? That's following a particular rule in a rulial multi-way graph, right? So that particular rule, just like in the case of the multi-way causal graph, that particular rule will have a particular causal structure.
Right. So here you're just showing that information by doing some specific particular type of highlighting. But maybe formally what this seems to suggest is that there's an additional space here. One is, of course, the structure itself, which forms a space by itself. But then there seems to be another space, which is some kind of trajectories of rules, some kind of trajectory space of rules. I'm not using the right terminology.
Yeah.
But so long as you keep, so that space is the one that is implicitly storing this highlighting information that you're having. So,
well, okay, so listen, there's ways to slice. Okay, so look, ways to slice things. There's the normal ways to slice things are foliations, fibrations, but maybe that's not enough here. Maybe there's something else.
Yeah, this might not be a standard foliation.
This might be a ruliation. Okay.
Because in foliation, so let's think for a second. In foliation, the goal is to look for space-like relations.
Yeah.
In
No, I don't think
vibration,
this is, yeah, go ahead. Yes.
in vibrations, the kind of entity is, well, what is it there? It's so here, for whatever we are doing, the relevant quantity is causality.
Right. Okay. So look, the objective of a foliation is reduce everything to a 1D sequence of slices. That's basically the idea, right? E.g., time sequentialization. You know, I figured out one thing. This is kind of obvious, but when I was giving some talk about something completely different yesterday, I figured out in Wolfram language, where we are doing this kind of one path evaluation thing, that is precisely a time sequentialization move. In other words, what we're saying is there is a multi-way graph of computations, but we humans, as users of that computation, want to sequentialize it. Anyway, that's just a micro observation. Okay, so we reduce everything to 1D sequence of slices, which is in which, you know, this is called, you know, take time seriously. Okay, and then I think we're going to see another thing here, which is take definite rule description seriously, which is, okay, vibration. What are we trying to do in a vibration? We're trying to, isn't it the case that in a fiber, we want basically this thing of having a definite, I mean, a fiber, if I'm not mistaken, well, explain, what is a vibration?
Well, I mean, okay, geometrically is just taking the base seriously, or is giving some identity to a base. Meaning that if you have, okay, there are two ways again. If you start with the total space, a total space has no fiber and base.
Right.
You denote something that you call a base, and then the rest becomes a fiber. And in a sense, a base is like making a slice. It's taking a section of it. So fiber from a total space, a vibration is really kind of sectioning something, but that sectioning can be done for various reasons. It's not necessarily only time. It can be that it preserves some invariant. In our case, okay, so now we can ask, in our case, what is this sectioning about? Now, it depends on which type of vibration you're looking at. If you're looking at the total space of the rulial multi-way system or ruliad, etc., probably the base would be a collection of rules, and the fibers would be multi-way systems themselves. In which case, you're sectioning over rules already.
Okay, so in this case, right, so in the ruliation, so to speak, it's like the base is laying out rules in rulial space, basically, then projecting forwards by the dynamics for each rule. In other words, what this is basically doing is saying, we've got all these paths, and we're going to lay out those paths. We've got a bunch of different possible paths. It's a little bit funky because of the initial conditions being, you know, did you get what I'm saying?
Yeah.
Yes,
because here, when you say projecting forward, what you're saying is you're just revealing causal structures, because the fibers are now causal structures.
I'm not sure I understand that statement completely.
So when you say projecting forward by dynamics, what is behind dynamics? Causal structure, right? What determines the dynamics?
Yes.
And after all, the goal of this ruliation, if the goal is to reveal causal structures, then you're laying out base spaces and then revealing and trying to, from that, disentangle the entangled structures, which in the limit you cannot see.
Okay, so you're saying the goal is to find a causal structure that, in other words, taking it a little bit more philosophically, it is what law of physics, well, I mean, what law of dynamics can explain what I see.
Right, right.
In other words, what causal structure, i.e., what causal structure corresponds to a certain aspect, to the aspect I pick out, I guess.
To the observed, to the observer's view, rather. Because
yeah, right.
depending on what the observer observes, there'll just be different causal structures that will seem apparent.
Yeah,
and accordingly,
right.
the observer will conclude one law of physics or another.
It's very beautiful, you know. Now, a question is, okay, so, and I think, you know, one can also move around in either branchial space or physical space, presumably. In other words, this ruliation is yet orthogonal to physical space. What on earth is the representation? Let's see. The physical space has to do with the way states are knitted together. The branchial space has to do with the way. Yeah, so go ahead.
Okay, just let me just add one small digression. Assuming that these towers that we are building up can in principle go to infinity, how about this? At the place where you wrote vibrations, if that really was a vibration where the base space is already rulial space in the sense that all the space of all possible rules, and the fibers are just multi-way systems coming from those rules.
Yes.
Then if we take that as one object, then this ruliation might be a space where you're taking an ensemble of those objects, meaning of all those possible ways of making base and vibration upon this total space. So it's already an ensemble. And there you're trying to reveal these causal structures by where the observer looks at one apparent universe or another, and the laws of physics are coming out. So in a sense, what you're writing ruliation is the ensemble of that fiber space already, in which there's a kind of higher level of fiber spacing to do.
Okay, and this is too complicated for me. Let me try and unpack this a bit. But let me ask a question here. So, I mean, my general picture is that different observers, okay, this has to do with basically the whole observer theory question, which I'm trying to, okay?
Right,
so,
but I think, okay, just to give some context, I don't mean to interrupt what you're about to say. What is the observer observing, or what total space are you placing the observer in? It depends upon that, right? In a trivial way, if your observer is just placed in a causal graph, and the observer's observable horizon is not beyond that, then that observer is not going to see anything beyond that. But if the observer is somehow placed in a way that that the observable horizon is in fact the multi-way system, then they will have some kind of sensing capabilities in branchial space. Similarly here, whether this observer is placed somehow within this fiber space, or whether this observer space lays in higher spaces, accordingly, you have to define what the observer is seeing. And through that, you will be defining what rules the observer is, what rules of physics the observer is picking up.
Notice the following point. We have to ask the question, what is our extent in physical space? 1 meter. What is our extent in branchial space? Unknown, but clearly doesn't involve all the quantum degrees of freedom of the universe, right?
Sure.
But
Yes.
but we have a certain sampling of branchial space. Then rulial space. How big are we in rulial space? In a sense, I suspect that our size in rulial space is, okay, so in a sense, claim size in rulial space of the observer is related to the uncertainty of inductive inference, I claim.
Size in ruliad space is related to uncertainty.
In other words, there are many rules given what
Yeah,
you
right.
observe.
Yeah.
There are many rules consistent with it.
So is that just really, is that some sort of rulial density as opposed to uncertainty?
Well, no, it's asking, it's saying how big is the region of rulial space?
Yeah.
Where we're saying, where we're describing rulial space, where how our coordinatization of rulial space. First point is we're assuming coordinatize rulial space, and this is where the fibration thing I think comes in by just saying different points assume different rules.
Mm-hmm.
Okay.
Right. So now what we're saying is, how big is the tube in rulial space that we exist in?
Right, but maybe this question can be, or this point can be slightly generalized in the following way. If you ask really, who is the observer, then really the most general answer one can think of is that everything is an observer with respect to its complement, literally.
Yes.
Right? So in that sense, every particle is an observer with respect to its complement. Every entity, every collection, every subset of all these spaces is an observer with respect to its complement, which has, the complement has to be well defined. I understand that. But what that means is the practical question, it's to ask better than, I mean, of course, we can always ask what is our extent, but one can ask what type of particles or what type of physical entities would be, or what property should a physical entity or a collection of nodes and edges, etc., have to have sensing capabilities of branchial space or rulial space of whatever space.
Mm-hmm.
So what would be, so for given background knowledge of quantum mechanics, we might be able to kind of almost fit and
I
say,
think the
well,
answer will be this. I think the answer will be this. What is a valid observer? Okay.
Mm-hmm.
Answer: something that in any
what
of
a
these
valid
spaces,
observer in which space?
in any of these spaces, something that maintains its integrity through time. It's a very important attribute, at least through time, right? Because the observer,
what time? Through its proper time, through its own time. It doesn't matter who else is observing, and that
yes,
can
that's correct. Right,
it doesn't matter if I see the photon decaying. The photon has to have its own
through
sense of
its time. Right. That's correct. Okay, so, and that, in other words, if the observer can't register experiences if the observer just self-destructed.
Mm-hmm.
Yes.
And so now the question is, what other attributes does it have to have? And my guess is, I think it's going to be this bounded, computation boundedness again, that the observer has some.
But that is a given, right? I mean, do you have an example of any entity or of this or subset of any of these spaces that are not computationally bounded?
Well, yes, we could have an observer who is, if we didn't have, look, if we just said the observer is observing complete foliations of the space, and those foliations are incredibly elaborate, that would be an example of a model of observer that is not computationally bounded. Or alternatively, let's think. I mean, the observer in the end is trying to do some form of compression. The observer, okay, so that's first point. Second point is many different states of the universe end up in the same state of the observer. i.e. the observer is doing compression.
Okay.
But now the question is, okay, now the issue is, can the observer do that compression with bounded computation? Okay, here's a case where they might not be able to. Let's say we're doing statistical mechanics and the state of the observer, the compression they're doing is, was the initial configuration of the gas on the left or the right? That is not something that a computationally bounded observer over time is going to be able to do. So there are only certain kinds of, okay, so only certain observations are accessible to a computationally bounded observer.
That's right, but I thought you were trying to make the point that there might be some entities that can do unbounded computation. I was trying to say that just won't exist.
I agree. It doesn't exist. Doesn't exist. But we can, but to think about, I mean, conceptually, we can imagine it, just like the anti-thermodynamic demon. So I'm saying, if we have the demon that can untangle the gas, then we've got something which is not computationally bounded, but which behaves in a different way. Okay, so now, okay, but I'm still trying to get straight. In rulial space, okay, all right, so explain causal structure for a second. I mean, in other words, we've got these states, and we've also got, okay, when we have a rule here, let's see. I'm trying to understand this, and I'm trying to understand it also in terms of these token event graphs, where causal structure is very clear, but where everything has been kind of atomized. Right? So the question is, for example, what is the token event graph version of this construction of rulial space? So I think the answer is, in other words, how do we add more rules? We have to add rules in which, okay, so I mean, in the case, token event graph level, rulial space. Okay, so the claim here is, if I take a random token event graph, wherever I had one, there I had a token event graph, okay? How do this is the full token event graph for this thing here. I think. Maybe it isn't. No, maybe it isn't. Maybe what I need to do is, maybe the point here is that I didn't have the right initial condition. That the correct initial condition here is, what do I want? Do I want 3 zeros here? Oh my God. And that's with token deduplication. Right, if I don't do token deduplication, I have to remember what the, this is why so annoying that the documentation isn't properly linked. Okay, token deduplication false. Okay, I don't understand this. Why are there only 2 zeros there? Let's try running it for more steps. Oh boy.
There's a third zero.
No, there was a third zero before.
Yeah, there's still a third zero.
Yeah, I know. But I mean, the question is, but why? is that 1 not deduplicated? Wait a minute, is this, am I computing the wrong thing here? Should I have this instead? No. Okay, who understands this picture? Right, so I've got these tokens, 0, 0, 0, they're all separate tokens.
Yes.
Right?
Yeah.
Now, I don't understand why that token, well, okay, let's see what happens if I say event deduplication as well. Absolutely nothing. Okay, let me try to understand what this did. So why aren't there 3 zeros at the top here? That's my first question. If I take, well, let's just add a 4th one and just see what happens.
Yeah. Okay. Well, there you go.
Oh, that's so frigging weird. Why isn't there another one of these? Okay, I don't understand this. Those are labeled 1 and 2. Okay, but the way that we would aggregate this up, the way we would aggregate this up is by allowing in here, assuming, you see that this isn't right because these are ordered strings. If we thought about them more like hypergraph rules, what we could do is we could add in here something that says, for example, another rule that says, for instance, 0, 0 goes to 1, 1.
Mm-hmm.
Okay, so now we have 2 goes to 2 rules here.
Yeah.
That get considerably more complicated. But the difference is, okay, but to encode states here. Okay, so in this case, the causal graph is rather easy to read off. The causal graph is literally what event connects to what event through these tokens, right?
Yeah.
The causal graph requires state decomposition, in the other case, to know what connects to what.
Mm-hmm.
So what do we conclude from this? I mean, what is the ruliad in a token event graph formalism? It's, in a sense, it involves graphs of arbitrarily high valence, I believe. It involves graph elements of arbitrarily high valence, right? Because it involves rules where the number of things going into a given event gets bigger and bigger. Correct?
Yeah. So essentially, so in a sense, this type of graph will be a bipartite graph, and yes, you want to trace pathways as this graph gets more and more complicated with more and more rules. You want to try to distinguish pathways with some kind of with some kind of property. In this case, possibly pathways where you have sequences of tokens and they alternate between tokens and events.
They always do that.
Yeah.
That's the nature of this graph.
Yeah.
Right. So I mean, but the point here is that the relationship between, the relationship between tokens, between events here is straightforward. That is, okay, so the question is, what is the limiting graph represented in terms of events? So this is a case, okay, so the limit of the states graph is the complete graph. Okay, what is the limit of the causal graph? I think it's much wilder. States graph. And the reason I think it's wilder, let's just look at this. Is it even, help. Okay, so is it the case that every event, okay, where i.e. every state can get to, i.e. there is a rule from every state to every state? Okay, is there a rule from every event to every event? I think not. See what I'm saying?
Why not?
Because
so how are you characterizing? So what you want to extract the causal graphs. Let's see. How do you want to characterize the causal graphs? In order to characterize the causal graphs, you want to trace some pathways within this. But to trace those pathways, you need to provide the set of some set of labels corresponding to what tokens you want to have along the progression of this path. So it's a bunch of tuples, right, that you're characterizing these causal graphs as.
yes, but I mean, well, insofar as states are made from collections of tokens. But let's just look at the simple limiting thing. So it's pretty obvious that the limit of the states graph is the complete graph.
Yes.
Right?
Yes.
Okay, so now what is the limit? And by the way, once it's the complete graph, it's kind of obvious that it has a groupoid structure.
Yeah, sure.
In fact, what is that groupoid? I mean, it must be some very well-known, i.e. what groupoid is that?
I would think if it's a finite, a complete graph with finite nodes, that would simply be a groupoid obtained from a so-called small category. It's not a very special structure, but.
Right, but I mean, this graph, is this graph like a Cayley graph for a group? In other words, is every possible rule like a generator, like applying a generator? That's not right. It's not right because, go ahead.
No, I was wondering, I was not too sure if that would be the case.
Yeah, I was wondering.
I don't think it is. I don't think it is the case. I think it's a different kind of graph. Okay, but I'm still asking the question. In the limit, in the kind of coarse limit, in which the limit of the states graph is the complete graph, okay, a very coarse limit. What is the analogously coarse limit for events? The problem is that an event, I really don't believe that every event is connected to every other event. I don't think that's how it works. Because the event is mediated by, let's think. Okay, in the limit, there are events which vacuum up. Let's not use the word vacuum because that's even more confusing, which ingest arbitrary subsets of the set of tokens. right? So in other words, what it's doing is it's saying, given the collection of tokens in all states, each event is, okay, so each events are mappings from subsets of the set of tokens to other subsets.
So
So
essentially, you're asking the question whether given such a graph or whatever be the structure on obtains in its limit, whether this set is fully reachable or not. Meaning that from any event, can one reach any other event or not?
yeah, but
yeah.
But okay, but so the first point is events in this setup, the events graph, the causal graph, is vastly bigger than the states graph. Because it's mappings from all subsets of tokens to all other subsets of tokens, which is bigger. I mean, looking at the states graph in terms of tokens, well, okay, so the question is, can states be made from any subset of tokens? Right? How are the states constructed? So one possibility is any subset of tokens is a possible state. Okay, so if that's the case, then we've got this sea of tokens. Oh, I see. Okay, if that was the case, right? Then it's the same thing. Then from the sea of tokens, the states are constructed. Every state is a subset of the sea of tokens, and there exists a rule taking it to any other subset. So basically, in both cases, the state-to-state transitions, not surprisingly, okay, given I see, given a state, my God, this is complicated. Right, so a way to think about it is the state-to-state transformation is subset of tokens to subset of tokens. Each event involves a certain subset of tokens, but it might be a different subset of tokens. So in other words, there's this mismatch between the subsets. Okay, so the state-to-state is subsets of tokens. And each events are also mappings between subsets of tokens, okay? Mappings between subsets of tokens. Events are also mappings between subsets of tokens. Not surprisingly, because each one of those, so a state on its own is a subset of tokens. Okay, but there is a mismatch. There is not necessarily a match between the state-to-state transformations. That state-to-state transformation could be a different set of, okay, so for example, let's imagine we have a state-to-state transformation, which is 1, 2, 3, goes to, so this is a state transformation, 1, 2, 3, the state 1, 2, 3 goes to the state 1, 4, 7. Okay, so that's a state transformation. Okay, now the event involved here might be the event 2, 3 goes to 4, 7, which is a subset, a different subset. In other words, this subset. So what we're saying is, and if we want to know the causal graph, this thing is mediating. Okay, there's a graph that comes, I mean, so the graph between all subsets. So if we just take subsets of a set, okay, here we go. Here's that thing. So then we're saying the state transformations are, okay, so those are the tokens. Those are their 4 tokens here. Those are the tokens. So the state transformations is a complete graph on those things.
Yeah, so those things
Right.
comprise some sort of power set of the initial objects.
Right.
And your state transformations are somehow all possible maps from that power set to itself.
Yes. Yeah, but you see what's happening with the events here is the events are subsets.
Yes.
The events are also transformations of this power set. But the problem
Right.
is
they are included. There's an inclusion map and one has to probably identify them.
Right, but my point is that it's a little bit non-trivial because the here, when we look at, there is an implied, okay, so this thing here, I don't know whether complete graph takes does complete graph take lists of elements? No. So what we have to do is we just have to say outer of directed graph. Oh, help. What happened here? Subsets there. Oh, directed edge. Okay, let's do it for a slightly smaller case. All right, there is our complete graph between those things. Now, the events that transform from one to the other aren't the possible events. Okay, so for any given state, there may be multiple events that transform from one to the other. So the events are of the form, this is also a map of possible events, right?
Yeah.
Because okay, but there's a complicated way. This is also a map of possible events. But the events embed in here slightly non-trivially, I claim.
Yeah.
Because, let's see, how do we draw that? So what we want to show is for every one of these edges, there may be multiple events. So we can also draw this picture. This is a state-to-state picture. We can also draw this picture. Oh gosh, this is complicated.
Yeah.
You know, we want a version of this picture. I see. What we want is a version of this picture in which each state-to-state edge is decomposed into events, is decomposed into possible events. But then those possible events have their own causal connections that are independent of the.
Right. Yeah.
So gosh. but then in the end, we're going to want to, and I know Xerxes, James said that you had to go at this time, which is a shame, but if you do, you will miss all sorts of exciting stuff. But okay, so the first question is this, we've got a minimal model here of some kind, which we still have to work out how it really works.
Yeah, but isn't the question that you were originally asking about whether the causal structure is connected or not boil down to saying that once you're able to have a good representation of this event-to-event graph, then you're asking whether that structure is path connected or not. If it's, or rather, when under what conditions does one ensure it's path connected or not? So if it's not path connected, then indeed what you asked earlier, that there might be disconnected causal structures within it. And if it's path connected, there's just one causal structure.
Yes. I mean, isn't that event horizons in real space?
Yes, but that's a ruliad space at a higher level, right?
Why?
Because this structure was, okay, let me think. So in the usual multi-way business, in the standard multi-way, there is already a way we understand disconnected causal structures. You cannot just jump from any event to any event. And that's the whole point of your usual multi-way system. Now, once you add extra rules and have all this built towards this limiting object, you get something. In a sense, one is asking whether that object itself, besides the causal structures which are sections of it as a whole, if it seems to have some higher level causal structure or not, and if that higher level causal structure itself has some disconnections through which you can disentangle the kind of lower level structures.
Possibly.
So it seems to be a kind of okay. So suppose at that level this is fully path connected, and for no possible rule there is a scenario where you get where you lose path connectedness. Then there is no higher level rulial structure. The ultimate structure is just a causal structure.
Okay, I've got an analogy. Okay, my analogy is computable numbers. Okay, so in the end, the computable numbers fill out the continuum, I think. I mean, to any degree of approximation, the computable numbers eventually, so the analogy is with sufficiently complicated machines, with sufficiently complicated machines, you fill out the continuum. Okay, but there is nevertheless structure. If you ask, what is the set of all possible computations? All possible computations eventually fill out the continuum. Although they do it in a very strange limiting way. But the structure that you get at any finite level, right, if the observer, in this case,
so long as you fill out the continuum, that's fine. That's not the problem. And it's also correct that until you get to that point, you're still having these kind of discretizations. But the point I'm raising is that once you fill out the continuum, what if there are disconnected components of that continuum itself?
I get it. Well, is that the case for the continuum? Here, well, you're saying because what we've got, unlike computable numbers, where it's just a machine generates digits, what we've got is something more complicated where we are dealing with mappings. And that's another thing one could imagine doing, right? Is analogy, not just individual numbers, but functions or mappings. So what happens in that case? What happens in the case where you're filling out? Okay, so that the question then is, if you look at Turing machines that define functions and they get to be more and more and more complicated functions, what functions are then defined here? And is it the case in your, presumably you can get to, right, I mean, you can do the same construction here. You can have functions between functions and everything. Right?
Mm-hmm.
And okay, so this is analogous. This is analogous to the creation of initial conditions. I think this thing about generating the original numbers is like saying, can you generate, what initial conditions can you generate? Can you generate all possible initial conditions?
Interesting.
Okay, so now, okay, but so what is the computable function? I mean, the computable function idea, studied at great length, right, there are certain hierarchies of computable functions, but to my knowledge, I mean, what is the topology of the space of computable functions? That has to have been addressed at some point. I mean, that has to be.
Yeah.
Well, it's a very important question, and I'm not sure to what degree it has been addressed, because, I mean, what we're pondering is whether or not that topology is actually non-trivial. And again, this is where these questions of computational irreducibility, et cetera, come into place. I mean, imagine if it was, if you could just get from any one location to any other location very easily.
Well, it could be arbitrarily far. It can be arbitrarily far.
Right.
That is fairly clear.
Right.
And that means in the limit, what a weird limiting space. But what's already known about the topology of the space of computable functions? I think Dana Scott was telling me he was thinking about that in connection with lambdas, but I didn't understand what he said. Topology of lambda calculus. I don't know whether that's relevant.
Thinking about it, like actually publishing, working on it, or just privately thinking about it?
No, I think he wrote some stuff about it. You can look it up.
Yeah.
Okay.
You can go and see Dana. He's in your neck of the woods.
Oh, really?
He lives in Berkeley.
Oh, yes, he's close by.
Okay, well, this is a useful analogy, I think, because this is saying, you would have crushed computability theory away if you just said, let's take the limit of infinitely large machines. And in a sense, okay, so yes, this is interesting. Okay, so algorithmic information theory. Oh, yes, this is very beautiful.
What are you going to say?
Well, I told you I had an intuition that it was all related. Okay, algebraic information theory versus NKS, like, computation. Okay, so here's the difference. In one case, this is a different foliation, effectively, of this space of computable numbers. In the case of algorithmic information theory, you're saying, okay, AIT says, consider, layers, kind of consider sizes of programs running for all time somehow. Whereas Well, let me think. This is a case where you're effectively going, I mean, you could imagine a thing where you're trying to find all possible results.
Yeah.
And you're kind of snaking back and forth between making more complicated programs and running for longer.
Yes, yes.
It's sort of a diagonalization-y type thing, that where you have, I mean, you could even say, given a particular state you're trying to realize, I'm not sure how useful this is, but I mean, let's see. What the heck is this ruliad thing? What is it? It's some, you know, let's see.
I suppose it might be instructive then to just take the example, one or two examples like this, like the space of computable functions, build a ruliad for that, and try to extract what sectors of that structure are precisely the programs and the things that are addressed by algorithmic information theory, and then you can show the entire kind of islands or open areas that are not addressed, that go beyond the stretch of that.
No, but look, in computable functions, this thing we're doing here is a way of enumerating computable functions. It's an incredibly pedestrian way of doing it, but it does enumerate computable functions, I think. It's tricky because I don't understand how partial functions work in this setup. In other words, oh boy. See, in other words, okay. So there may be a thing. Yes, here's the point. Okay. In constructing all possible functions, some are easier than others, i.e., given a particular basis, some functions cannot be computed in finite time.
Sure.
Right, but those would be the non-computable functions.
Indeed, with respect to that basis.
Yeah.
But by the time you've gone up and looked at all bases, you've got all functions. Or is that not the case? Are there still absolutely undecidable things? Oh, I'm really confused here. I mean, in a sense, this is saying that you reach every oracle by, if you just enumerate arbitrarily complicated machines, eventually to some level of approximation, you will cover every oracle.
So I suppose the catch is if you are able to construct arbitrarily complicated machines. That
well,
itself,
I know, but we're saying that that's the case. But the reason you can't do that, all comes back to the observer again.
Yes.
Right. Why can't you construct arbitrarily complicated machines? Answer, because the observer can't prepare such things, can't prepare /sense / whatever. That has to be the so in other words, in Greg's algorithmic information theory thing, let's think. In my setup, one is saying that effectively the observer, the scientist, okay, so the NKS setup, the scientist can only, what is the verb for induction? Can only get from induction.
What, induce?
I don't think it's the right verb.
Mm.
Can only get from induction to fairly simple rules. So that would be the claim, that the description of the world, sort of the NKS meta implication is, let's see, whereas
right, but that is in a way the reason why I was saying before that there might be disconnected components of the continuum. In a
Yes.
sense, each is defined by the type of machine that an observer can build. Now, if this observer was really unlimited, totally resourceful to all extents, then sure, they would be able to fill all the gaps between these components, and that's it. But this is
Yes.
precisely the reason why that wouldn't happen.
Right, but what this is saying is, while the full ruliad in some limit is like the continuum, there is incredible structure that is imposed. There is apparent structure imposed by the fact that the observer is bounded in some way.
Mm-hmm.
So in other words, while the ruliad contains the whole continuum. So the analogy is,
Yes.
The ruliad contains the continuum from the point of view of an observer outside the ruliad.
yeah,
No
exactly.
observer within the ruliad can see this whole continuum.
Right. Within the ruliad, any observer must be bounded.
That's nice.
Yeah.
That's nice.
So can't see the whole continuum.
Oh,
So
very
therefore
nice.
sees some slice. So the analogy here with computable numbers is let's see, if you believe that you're constructing the computable numbers, sorry, you're constructing the continuum. I'm a little confused by how this is working. What's the analogy between this and the computable numbers? In other words, you've got the continuum of all numbers, of all reals, and now what does it mean that there's an observer who can only get to the computable numbers? Oh, it's very simple. It's very simple. Look, analogy with computable numbers, the observer has to have a way to get into their mind the whole sequence of digits for a number.
Mm-hmm.
And that can only happen
Yes.
if the number is computable with a finite size machine. Because what the observer is getting into their mind as the compression as their model of this number is that
the observer
machine.
is the machine in this case, rather a finite size machine.
Well, or the observer has, I don't know whether the observer is the machine. The observer's model is the machine.
Okay.
Stephen, I have to step out for about an hour. I presumed that Xerxes would have had to have left like 20 minutes ago.
I would be leaving very soon, in fact.
How
You
do you
guys
want
are leaving a cliffhanger here. How can you leave such a cliffhanger?
That's why I've been cliffhanging.
The ruliad, but the ruliad it'll still be here when we reconvene. Stephen, when do you want to continue this conversation?
Well, as soon as we can, but I have constraints today.
Can you meet after 4 p.m. Eastern time?
I could meet at 4 p.m. Eastern time.
Xerxes?
After 4 p.m., yeah. So that's my 10. Yeah, I could meet at 4.
Okay.
Actually, just to be safe, I'd prefer if we can make it 4:30 or something.
Well, we'll start at, let's say, 4:15. Okay, and then you may or may not be there for the beginning of the cliff.
Okay.
Yes, we'll see how We'll see where we can get in 15 minutes. Now that we're already at
This
the
is
cliff.
getting really nice. This is getting really nice. This is the kind of thing I was expecting. That there's an understanding of the ruliad in terms of, I've been saying this for weeks, right? In terms of Chaitin-esque thinking, so to speak.
Or at least trying to compare our own approach to the Chaitin-esque approach.
Well, no, but I mean, but his way of thinking about yeah. Well, anyway.
Let's continue this.
Okay,
Yes.
to be continued. All right.
Okay.
See you guys in a bit.
Cheers.
Okay. Bye.
Bye.
I think that it's very much like the story of the continuum. I think the continuum is a very good analogy to this. That is, from outside, you've just got all the rails. From inside, you are but a Turing machine trying to compute these things.
Yes, I see. Yes, I understand. Well, I suppose, but the question that I have is then, I mean, I've been thinking of the ruliad as this all-encompassing notion, but if there's some observer that's outside of it.
No. There's some conceptual observer that's outside of it. And we, in even having a discussion about the ruliad, are looking outside it.
Right. But
Right?
what's outside the ruliad? That's the question I wanted to ask, is that it's not all encompassing.
It's like saying, we can have a discussion about the whole universe, even if there's nothing outside the universe. If you live on a sphere, you can have a discussion about the whole sphere, even though all you know is its surface.
Yes.
If you can't count to infinity, you can still have a discussion about infinity as a symbolic thing. You can reason about things. I mean, this has to do with constructibility and so on, which we are about to come to.
Yes.
I mean, and the notion of constructivism and so on. But I have a different question for you as we wait for Xerxes. Oh, by the way, this is an important point that I just realized. This is another feature of consciousness. The fact that we parse the ruliad by assuming that it has consistent rules is another feature of our consciousness.
Well, yes. Imagine if we didn't do that, right?
Yeah, exactly. Right.
Yes.
Then no science is possible. We can say nothing. We are. But now we have to think about how operationally, what would it look like if, in other words, basically what's happening is, we are tracing those aspects of the universe that are successfully described, that can be described by a particular rule. By a particular rule or bundle of rules. Okay, so this is a point, I've got a couple of points I wanted to make. I claim it's a feature of consciousness that we follow a single thread in the ruliad, because it is our ability to describe the world in a consistent way. So in a sense, we are tracing those aspects of the universe that can be described by a particular rule or bundle of rules. There may be other aspects of the universe, but we, with our particular methods of perception, are simply not sensing those things. Xerxes is silent. Do you see what I'm saying? It's the same type of thing as saying we operate in a certain reference frame that sequentializes time, and we don't get stuck in these multiple, in all these different possible threads of time, possible threads of history.
Yeah, but that's something we also expressed at the level of multiways, right? Are you now saying something different in the sense that you want an extrapolation of that statement at the level of the ruliad?
That's correct. I want at the level of the rulial multiway system. So what I'm saying is that in the multiway system, and we need to get this a little bit more precise, okay? So in the multiway system, our interpretation of quantum mechanics is that we believe that definite things are happening, right? And that therefore, even though there are different branches of history, we somehow pay attention to, we are somehow sensitive to. So I mean, in the quantum mechanics case, the non-rulial branchial case, the just pure quotes pure branchial, single rule branchial, fixed rule branchial case. Okay, so in that case, what are we saying? We're saying there are different threads of history. but we conflate different threads of history to get a definite history. And somehow causal invariance makes it consistent to do that.
Mm-hmm.
Now, when we say we conflate different threads of history, what are we really meaning? What we're really meaning is that it's like an averaging procedure, similar to, when we say conflate equals averaging / whatever else. That's what we are simply sampling. We are a finite size in branchial space. And therefore, our finite size in branchial space causes us to aggregate multiple branches of history. But there are probably branches of history that we simply don't pay attention to. I mean, this is something I haven't really thought about before, but I mean, let me think about this for a second. I mean, are we imagining? Okay, so simplest model, CF, the causal case, a space-like hypersurface which covers the universe. Right?
Mm-hmm.
So in other words, a simultaneity surface that is universe-wide, simultaneity throughout all space. So that's our first model. But clearly that's not the only thing we're doing, because in the causal case, we're actually trying to have, coordinate patches and all kinds of things like this. That's how we get dynamics, is by looking at not just having special relativity, right?
Mm-hmm.
So how do we think about the fact that this is special relativity, right? This is i.e. special relativity. Okay, so the analog in quantum mechanics, analog in QM, I claim, is special QM, which is basically, i.e., quantum mechanics, pure quantum mechanics, not quantum field theory. I claim that that's the analog of special relativity in quantum mechanics. What do you think of that claim?
So sort of relativistic quantum mechanics.
Well, but what I'm saying is, what that's doing is, in ordinary / special QM, one is saying there's a single quantum state. Well, it's not quite a single quantum state. There's a single, well, it is a single quantum state, actually. It's just superpositions for the whole universe. Right? We're not allowing the possibility, just an analogy to this case, the causal case. We're saying we're setting a time thing that covers the whole universe.
Mm-hmm.
We're setting a time surface across the whole universe. What's the analogous thing in rulial space? I think it's something that is very bizarre for us.
Well, already this object is a little more subtle, right? This, what you're calling special QM, because for the previous case, it's a causal graph. Here, there is obviously, after the fact that the observer has done this averaging, etc., there is some kind of induced causal structure induced by the observer that is there. And so there is a new causal structure that is the basis of the special QM. And this involves entangling states between branches and then developing that whole thing across some sequential time.
Maybe. I mean, I'd be enough, look, I'm thinking about a pure multi-way system without any spatial degrees of freedom, where you're not describing the states in the multi-way system as having any kind of spatial characteristics.
Okay.
So
Right?
But even then, if just as the causal structure in special relativity is ignoring the states is just some causal sequence, let's say, for simplicity, I can just think of it as a simple sequence. Now in special QM, you do have some sequence. The only difference is that the objects of the sequence are now conflations across branchial space.
Exactly.
Right.
There is a sequential evolution in time.
So this is what I mean by this
of
causal
superposition
structure.
states.
Yeah.
Right.
You can call it the causal structure of superposition states.
Right, but what it's saying is the observer. Look, the observer says, no, I mean, what we're imagining is this is just a superposition. The observer, and insofar as the observer is
so if you remove time from this, then it is just QM, right? It's almost stationary QM, sitting at a point, having entanglements, having superpositions, QM, that's it.
Yeah, right, that's right.
Now, when you allow this, these constated states to develop in the observer's time frame, that's when you get special Q.
No, I think it's just ordinary quantum mechanics. It's just the time evolution of quantum mechanics. I'm not imagining it's anything different from that. I'm simply saying that to get the time evolution of ordinary quantum mechanics, I'm saying what you do is you have to define what time is. And what you're doing there is basically doing, I mean, to give an example, let me see if I can find it. By the way, you are making a lot of clickery. I think that's James is clickerating, making a sound which corresponds to a click of some kind.
I think James has something in the background.
That's what I'm saying, yes.
It could just be a thinking sound. Is it this?
It's that.
Yes, that's just a tick. But I can disengage it.
Oh, interesting. I haven't encountered things that make sounds when they think since the very first computer I used. Okay, in any case. So this is something, I mean, the concept here, not very excitingly portrayed in this picture, is that you have to decide what sequence of superpositions you are thinking about.
Right.
And in quantum mechanics, a different choice of this foliation is some kind of, what is it? It's a different basis set?
I don't know, think it's a different basis set. It's just the usual way relativistic quantum mechanics works, right? It's just taking a quantum mechanics within the reference frame.
No, there's no space here. This is not space. This is purely branchial space.
Yes, but when you're foliating, you're making some choice of time.
That's correct, but you're not making a choice of space. I think the choice of time, I think choice of foliation is to do with the basis that you're using for is question mark, like choice of basis for quantum states. I think it's more like that than having anything to do with relativity. I think that the statement of relativity for pure quantum mechanics I'm going to claim that the statement of relativity is that you can make a change of basis, but that there's a limit. Yes. Okay. So I'm going to claim there's a limit to change of basis determined by the maximum entanglement speed. That's what I'm going to claim. See what I'm saying? That is that if you start saying if there's a basis where the Hamiltonian, you get what I'm talking about? I mean, in other words, you can only tip the time so far before you get faster than the maximum entanglement speed. What consequence does that have? And how do you see that in ordinary quantum mechanics? I think you see it in ordinary quantum mechanics. Let's see. In a many-body quantum system, there are many quantum states. James's tick is well alive and well. I'm now almost curious to switch on video to find out what the tick is. We're giving him a hard time. I don't want him to feel self-conscious about. But you get, do you get what I'm saying here? That I mean,
yeah. I mean, in a sense, what do we do when we are talking about change of basis in special relativity? We have a coordinate of space-time in that case. We define and there is the Lorentz transformations on it, which take you from one basis to another. Now we have a larger space which has the spatial coordinates plus some branchial coordinates. And now one is performing some generalized Lorentz transformations within that space, which has to now respect not just the speed of light, but an additional speed of entanglement.
No, I think that you don't need the spatial degree of freedom. I just don't think you need it. I think you can just discuss this purely in terms of quantum states. You've got a giant layout of quantum states, okay? And the question is, the Lorentz transformation, how do we make a quantum system where there is an obvious layout of its quantum states, an obvious branchial layout of its quantum states? Is that something we get in like a spin chain or a quantum circuit with wires? Okay, so let me make the following claim. Consider a quantum circuit with lots of wires. Okay?
Yeah.
Then consider the timing for the circuit, right? So you could have something where you say every gate on these wires is being clocked at the same time, right? But you probably don't have to say that. You probably can consider there to be a tipped reference frame in which the different wires are, assume the wires interact only with their neighbors. Now, unfortunately, it's an exponentially more complicated space than that. But you get what I'm saying. I'm saying, imagine that the timing front. There's one timing front, or you can tip the timing front. Do you see what I'm saying?
But are these states entangled across these wires?
Yes.
Right.
Yes, they're entangled by virtue of the fact that there are interactions between wires.
So there's like a spin chain in branchial space, you mean?
Yeah. But so the thing is, they're entangled across the wires. But imagine you could lay out the states in branchial space. Okay, so we have all the states. We have, for example, here are all our states. Naively, here are the states of n wires, 3 wires. There are the possible states of 3 wires, right? Exponentially many states. Question, how are these laid out in branchial space? Answer, it depends on the interactions.
Okay.
The interactions knit together branchial space.
Okay, yes.
But I mean, a simpler thing, even if you want to take these things as though they were different entities, if you were just to take, for example, a quantum particle, that already is satisfying this example. It has, let's say, several up-down intermediate states. It could be one system, whatever. It is already something that is laid out in branchial space.
I don't quite understand that. So a single particle, okay. So alternative case, a quantum particle. Okay, and so then the idea of the quantum particle is, no, it's not true. It's not true, because a quantum particle, consider it distributed across X buckets, across points in space, right? So in a sense,
points in which space?
Physical space. That's what a particle does. That's why it's interesting to be a particle. Particles exist in physical space. They might also exist in branchial space. That's a different issue. Okay, so we say if it's distributed across points in physical space, then, for example, it might have 1, 0, 0, 0, 0. It might have 0, 1, 0, 0, etc., 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 etc. Many possible configurations of its wave function. Right?
Okay.
Now, but again, there are superposition cases in which it's not just a particular position in physical space. It's it's really not that different from this case here. Right? So now the question is how these are laid out. The whole point is that because of the interactions, okay, here's the point. Entanglement cones. Interactions / entanglements define the geometry of branchial space. Effects can only propagate through interactions.
Okay.
Hence, it is self-evident, basically, self-fulfilling, that in branchial space, there is a finite speed of propagation. Insofar as there's a finite speed of, insofar as the interactions are somehow local. right? The interactions are defined to be local because they are between these points in branch Hill space.
Mhm.
Okay, so now what is that noise? It's very odd.
What noise?
Well, that's the problem. It's a kind of a, I don't know. It's as if sometimes when speaking with amply bearded people, you hear noises like that.
It's like those jingling toys.
That's what it sounds like roughly. Anyway, okay. In any case, doesn't matter. But okay. So the question is, what is a Lorentz transformation here? How do you make a Lorentz transformation? I think you make a Lorentz transformation by, again, the timing front on the quantum wires. And this is saying there is a maximum tipping of the timing front on the quantum wires.
Mhm.
You can't tip further than is allowed by the rate at which effects can propagate across branch Hill space. Now, why can't you tip? Why can't you make a frame? What happens in, oh, I see. The reason you can't make a frame, in the usual case, the reason you can't tip more than that, yes, if you tipped further, you'd end up with time-like separated objects, time-like separated events in the same time slice. Right? That's the thing that goes wrong.
Mhm.
Yes.
Okay, so now
this is all an exercise in starting to think about rulial space, though, right?
also, well, it has a subtext, which is understanding quantum mechanics. I mean, and this is,
well, but my question is, what is, I mean, we have branch-like, we have time-like, we have space-like
separation.
Yeah, what's rule-like? Right, exactly.
It just means that the universe is evolving according to different rules. Rule-like separation means that you took branch-like separation is you took different branches of history.
Yes.
Rule-like separation is you took different assumptions about what rule is used.
Yes.
So there's a translation cone, which is exactly that, the same kind of thing that we're talking about here.
But do we need anything like a rule-like hypersurface or anything like that?
Yes, absolutely we do. We are about to get that.
Okay, good.
And as you see at the bottom of the page, look at that for an exotic concept.
Yes, we will get there.
What is the Rulian analog of quantum effects? So I suspect, possibly, there are discrete possible descriptions, not a continuous variation of possible descriptions.
Of what?
The universe.
Are we treating rules as descriptions?
No.
Then
Well,
what's the description?
The assumption of the use of a particular rule.
Okay, that's quite close to, I think, what I was just saying.
Yeah, it is. It is. But I mean, the question here, are there rulial quantum effects in metamathematics?
wouldn't that happen when you start conflating rules, when the observer starts conflating rules?
One would assume, yes. But walk me through how that works. What causes a quantum effect in the usual case?
Okay, so in the usual case, by quantum effects we mean, so there, on one hand, there is the fact that there are spaces which are separable, at least in the sense of their causal structure, and then there's a issue of measurement, which is then conflating those some of those states across branches of history.
Mm-hmm.
And that's what we think of in the usual quantum mechanics story. So that idea can be generalized across other structures or higher structures of the multi-way system. And in the end, it's sort of all related to the various notions of time that observers at different levels can be seeing. And in order to maintain that aspect of time that is ingrained into that observer's consciousness or whatever, there is some sequentialization at different levels of the tower of these systems that observers keep doing. And every such sequentialization is a quantum mechanics at that level.
I think that's correct. But I mean, how does it deviate? How do we see a deviation from classical? Okay, quantum effects, basically, it is, there are multiple paths of history. That's the core of the quantum. That's the core of quantumness.
So maybe what I was trying to say is that there is not actually one quantum mechanics. There's a hierarchy of quantum theories.
Oh, I agree. Yeah, I agree. And one of them is the one that is our traditional branchial one, where it's just different events occurring in different, in different orders in a single place, in different places, etc.
Yeah.
Right, but the question is, what is that noise? It's just driving me crazy. It's kind of like that meditation. That's scraping.
Well, I hope it's not my microphone. I mean, it seems as though I'm sitting completely still.
Well, it's as if the microphone is rubbing against something. Anyway, bushy beards are a possible suspect.
Well, yes, I don't have that.
Yeah, okay, well, fine. The virtual beard.
Now, wait, okay, so.
And you see, you are making me make stupid noises too, because I'm doing something more ridiculous than you can imagine. You can figure out what's making that noise.
What are you doing?
I am doing something that I often do when I'm concentrating, which is I tear off strips of paper and I start chewing them. Okay.
Oh, okay. Well, that's
much worse than many other things. It's kind of the.
I used to do that when I was a kid. Yeah.
Well, I didn't do it when I was a kid. I started doing it when I was a deep adult. So I don't know what that tells you.
Well, you have more privacy as a deep adult than as a child, so you can get away with doing that kind of thing. Well timed. Now, so with the rulial analog, with the quantum effects in rulial space, you're saying you can't necessarily conflate two rules. This is the point, right?
I didn't say that necessarily. I wasn't there yet. I was simply trying to understand, in ordinary quantum mechanics, I want to know where H bar comes in.
Oh.
Okay. There are multiple paths of history, but, fundamentally, somehow the distance in branchial space is the elementary time times the maximum entanglement speed. And I'm trying to ask, when do we get to see that there are multiple paths of history? So we don't see multiple paths when we as observers are so coarse that we average over them.
Yeah.
Okay, so when are we not so coarse that we average over them? There are really a couple of cases. One is the paths manage to separate. You know, we see the distinct paths when they are far separated. What causes them to be far separated? I think it is an essentially topological effect.
Yes. Yes. I agree.
Yeah, but where's the H bar? What causes? What is the essence? Here's the thing I just don't know. If you say, I'm in 1920 and I want to observe quantum mechanics, what kind of a thing do I need to do to let's say I'm trying to observe the path integral. You know, it was interesting. I was reading a review of the Feynman and Hibbs book, a contemporaneous review of that book that was really dissing it and saying the path integral is an interesting way of viewing quantum mechanics, but the book spends most of its time proving that it's just the same as the usual way and there doesn't seem to be any advantage to it, and it's hard to compute anything in it. So here's what I'm going to ask. Let's say you're back in 1940, whatever, and all you know about quantum mechanics is the path integral. The question is, how do you validate that the path integral is correct, as opposed to just the least action principle where you just take the extremum? What experiment, what experiment immediately shows you the validity of the path integral?
So I might not be remembering it completely, but isn't this Berry phase the type of experiment that would be particularly
possibly, yes,
prone to catch these type of paths that you go through?
Possibly so.
So I think they have this vector potential, and then how you go across it, you pick up this phase.
That's correct. Well, usually you can't measure the vector potential, but in that phase you can measure the vector potential. Yeah. I mean, there's a much simpler one, which is diffraction. As soon as you observe interference between the two slits, right?
Yeah.
Shows that basically you are, let's see, what is that showing you? That is showing you oh my gosh, this is so confusing. See, at this point,
in a way, that's correct, right? So the kind of standard interpretation of the double slit is that one shouldn't be thinking of it as particles, but as waves. But what waves really are, you could just think of them as trajectories of individual, collect bundles of paths rather.
Yeah.
And those bundles of paths are literally what the path integral is talking about.
Exactly. Yes.
Of course, there's the pilot wave interpretation, which is close to that. But at the end of the day, that's really just talking about the path integral, taken more seriously, like literally ontological.
Explain.
So instead of thinking of a pilot wave, you can just think of the path integral as if there are these multiple paths that are coexisting.
And the paths actually have an ontology.
What is the pilot wave thing? What is the Bohm thing? I always forget how that works. What is the idea there?
So I think over there, the idea is that so there, of course, there are some confusions there. They are not thinking of any external space like a branchial space or anything. They think of everything within our usual space-time. But they try to give some more kind of ontology or some reality to the wave itself. They're not thinking of it as a probability wave. In some way, they want to assign some realism to the wave, and then they want to think of the spread as if there really is something. I don't.
And so they're right, but in the wrong space. If they had set
exactly.
themselves up in branchial space, they would be cooking
exactly.
wrong.
The confusion is because they are trying to box everything into 3+1.
Yeah, that won't work. Right. But so the point of the double slit experiment is that things far separated in branchial space wind up being close in physical space.
Mm-hmm.
That's the essence of what's going on. By the way, we really should do more carefully the Jonathan, etc. double slit thing, because I think we're getting close to actually understanding how that works. Despite its controversy, doesn't mean we should avoid the topic forever.
No, the double slit is a very kind of, it's a pathway to quantum mechanics. It was, and it probably will be even for us.
Yeah, but the point about this is the observer the point is, okay, the claim is, if the picture is the observer aggregates all path weights within a certain region of branchial space. And the claim would be that, for example, the destructive interference comes about because the observer's region of that basically things escape from the region of branchial space that the observer can pay attention to. Let's think about this at the end for a second. So I'm rather taken with the idea of a Lorentz transformation for quantum mechanics and being able to formulate that for a big quantum circuit.
Yeah.
And basically the concept there is, imagine you have a, quotes, homogeneous quantum circuit. I mean, it's effectively multiple identical wires.
Sort of a tensor network.
It is, yeah, it's very similar to that. Homogeneous in branchial space. Okay, now my claim is, how do you move? How do you change speed in branchial space?
How does what change speed?
The observer. Because that's what we're talking about here.
Put some constraints on what is being propagated?
No, I mean, what we're saying is, we're saying, imagine the timing front as it goes down the quantum wires.
Yeah.
Okay?
Yeah.
Okay, but boosts, you can think of, rather than changing speed itself, you can just think of all these as some kind of generalized rotations. In the same way, like boosts are rotations between space and time, now you have rotations between branchial space and time, or branchial space and physical space. You have a combination of such rotations, or rotations that are involving all three.
Right. I don't understand the rotations in branchial space and physical space. Also,
yeah, so for now, we can just think about branchial space and time as opposed to physical space and time.
yeah. Okay. So, but how do you actually do it? Like in physical space, you have a rocket and you fire your rocket thrusters and you start moving through physical space. Right? How do you move in branchial space? Answer. It has to do with the measurement that you're making. The reason, the way you can do a boost in branchial space.
That's what I was trying to say before. Yeah, okay.
Right. So basically, yeah, the answer is you are going to measure over time, you are going to measure all wires. Or you're going to measure some set of wires. At what time do you measure each wire?
Mm-hmm.
And basically, if you say, I'm going to zip my measurement across the system faster than the system itself can
propagate.
Can propagate information.
Yes.
Yeah. Then what will happen is you will end up what will happen then?
But
Go ahead. You have to end up with there can be two updates. There's an ambiguity in what you see. Yes, there's an ambiguity in what you see because you get to that wire, let's see, before the wire has updated itself. A very useful description.
Well, surely there's some case for computational irreducibility to be made here. This is the point, right? That you can't.
I don't think so. You can get
you can't outsmart the. You can't predict what's going to happen.
You can get relativity. Okay, you need computational irreducibility in the special relativity derivation to deal with the fact that that you're not seeing the details of the underlying structure. You're not seeing I don't think you need that here. I think that the okay, just to understand this physically.
Mm-hmm.
What is the device that measures all these wires? I don't even know how any of this stuff works. This is the frustrating thing. I have got to learn this stuff. I've got to learn it. I mean, most of the time, the measuring device is just an amplifier. And in a sense, quantum mechanics, this is actually a point that I was going to make. Quantum mechanics happened when people invented amplifiers.
So here, let's say that you have your network has your quantum network has some states which can be spin states to make things simple, and then you have a Stern-Gerlach device, which you want to run through all these states.
Yeah.
So the problem is, how do I actually take this device in branchial space?
What do you mean? I think that, look, all you're doing is you've got these different spins. No, it's the different spin configurations. You are measuring against different eigenstates.
Mm-hmm.
Or more accurately, okay, and you're measuring
at a given time. This device will collapse the function into one of the eigenstates.
Well, I think that's this picture here. That's what it looks like when it collapses. That device is freezing time.
Yeah.
I don't think it can freeze time for everything. Yeah, you see, I think what has to happen is, okay, it's kind of, freezes time for a particular set of states. Or a particular template, more accurately, but we can assume it's just a particular set of states, and it's 0 for all the others. Freezes time for a particular set of states. Then one freezes time for a different set of states, etc. And so I think the limit of that is just one of these foliation lines.
You mean by limit, you mean how many states it can freeze? I mean,
Yes, yes.
how many states it can pick up when it's freezing time?
No, I'm saying that as you move around this freezing region,
Mm-hmm.
if the freezing region is small compared to the whole thing, it's as if you're just describing it freezes here, it freezes here, it freezes here.
Mm-hmm.
Okay, so wait a minute. As you look at different quantum states, there is a certain rate Should this be computable in ordinary quantum mechanics? I mean, the maximum entanglement speed seems to require another fact about the discreteness of time and so on. Well, okay, in any case, okay, so my little exercise here is, well, it seems like in quantum mechanics, one is averaging over a certain number of branches of history.
Yes.
In rulial space,
Mm-hmm.
does one average let's think. So, I mean, in branchial space, we could say we are only going to pay attention to a single thread of history. That's probably unrealistic for a coherent observer.
Okay.
So we're forced to pay attention to a bundle of threads of history somehow.
Mhm.
What would it be like if we're paying attention to a bundle of, see, I claim that it's just the limits of inductive inference. That to say that we are considering a bundle of rules for the universe is to say, oh my God, you know what? It's just amazing how there's no wrong theory. In the following sense, okay? People make the claim there won't be a fundamental theory of physics. This is a version of that claim.
Yes.
Right? Because this is saying is, you know, maybe there, quotes, is no fundamental theory of physics because we are spread across a bundle of histories in rulial space.
Mhm.
And we can only distinguish them, and we don't nail down a single one because we are limited by our finite experiments in doing inductive inference. In other words, what we're saying is there are many theories of physics, and we cannot distinguish between them using finite experiments.
Right. I mean, the only way to distinguish would be to get out of the system.
Right. But the fact that, so then the reason we think we believe the universe has definite laws is because we're ignoring everything that doesn't relate to the laws we care about.
But what if there are rulial quantum effects? Then would it be the case that every once in a while, the thing that you're ignoring makes some sort of appearance?
Yeah.
Yeah. The revenge of the continuum happens in rulial space as well. You see, if there are some quantum effects, then it does, that's relevant to this question of whether or not there's a fundamental theory or not. That would be important.
Why?
Well, because even if, for the most part, it's tenable to basically ignore everything that doesn't relate to the laws of physics we care about, even though that's probably fine most of the time, it might not be.
Yeah, okay. So the
fine
question
all
is,
the time.
can we construct a potential experiment that's the analog of the double slit experiment?
Oh, wow. Okay. Wow. Double slit experiment for rulial space. Okay, well, let's think about this. We
Okay.
said of the double slit experiment,
It's just things going in different branches in branchial space.
well,
Different
that's what I was going to
threads
say,
of
right?
history.
So what's the branchial space in rulial space? I mean, if in order to have an
It's
experiment,
things going according to different rules of physics, laws of physics.
well, okay.
And the question is,
Mhm.
But an observer is anyway going to conflate them, right?
well, that's what they try to do for branchial space, but they don't succeed in the double slit. The whole point of the double slit is that the observer doesn't succeed in conflating things because the things get too far away in branchial space. The histories are too distant. Why does that happen in branchial space? What causes them to be distant in branchial space? And what causes things to be distant in rulial space? I mean, honestly, the main thing that would happen in rulial space is some effect occurs. It's like turbulence, you know, it's grinding things up. Or like, yeah, it's like thermodynamics. It's like, okay, here's the claim about rulial QM. In statistical mechanics, mechanical work is ground up into incomprehensible heat. Okay, but that's only a particular kind of mechanical work.
Fine.
Let's think about this for a
I
second.
mean, are rules separated by the amount of computational work it takes to translate from one to
Yes.
another sideways?
Yes, 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 yes. Yes, indeed.
So the double slit is some experiment where you want to see you're testing computational work to translate between different rules.
Yeah, I mean, depending on which slit the thing went through, it's following different rules.
Yes.
And we can't successfully conflate those rules together.
Yes.
But the issue is, how do we end up with okay, but let's just follow through the statistical mechanics analogy.
Yeah.
Okay.
Yeah.
Mechanical work is normally ground up into incomprehensible heat.
Yeah.
There might be another kind of mechanical work let's see. It's as if one is escaping from a circumscribed area of rulial space.
Mm-hmm. What, to another?
Yeah, to one that one is no longer to one that our consciousness is not in. So that's okay. Motion in physical space. The aliens are escaping in their spacecraft. They're going to a region of physical space that we're not in.
Yeah. Okay.
How the hell do you, I mean,
how do you do what?
No. Things move in physical space. You have a flash of light. It goes out in all directions. Something happens in branchial space. The effect goes out in all directions.
Okay.
It's the observer that goes in a spacecraft in a definite direction in a first approximation.
Okay.
So an effect in rulial space yeah, I mean that's what we already know. There are, rulial light cones where one effect, by virtue of different sequences of rules, reaches other places.
Yeah.
And well, I'm just trying to think about what I want to come back to this first statement. There is no fundamental theory of physics.
Mm-hmm.
Because the claim would be to know which branch of rulial space you're in, you have to do an infinite amount of inductive inference. Now, what this is saying, in the end, what this is basically going to say is, we have solved pre-physics. And the rest is all a story of describing us.
Mm-hmm.
What's the analogy in metamathematics?
Of what?
That statement.
What's that we've solved pre-physics and the rest is just a matter of us?
Yeah. I mean, I think it's the same thing in mathematics. It's like we have this raw axiomatic system,
Right.
which is essentially the ruliad.
Yeah, then the rest is just model theory. The raw thing is the syntactic code.
Yeah.
And the rest is just models, literally model theory. Of course, the only issue there is that the reason they say that there is no fundamental axiomatic frame of mathematics is because you can define that syntactic thing under various axiomatic schemas.
Mm-hmm.
Okay, so the claim is there is no fundamental theory of physics in the same sense that there's no fundamental theory of mathematics.
Mm-hmm.
So there's no theory of everything. There's just a theory of our thing.
There is. There's a theory of the ruliad. It's a theory of the everything.
Okay.
But it's only a useful theory of someone outside the ruliad.
That's correct. Within the ruliad, you have to have a theory of yourself.
Exactly.
This is very beautiful, actually. It's also, it feels correct, because one of these things where there's never a, hold on 1 second. Ugh. Okay. I have to leave in 40 minutes. Okay. So wait a second. We were talking about the fundamental theory of mathematics. We're saying that okay, to know what our physics is like. In other words, there is a fundamental theory, and the fundamental theory. Okay, this is the same statement as we keep on making about the ruliad itself. That viewed from the outside, the ruliad is kind of boring. But any reference frame of the ruliad from inside the ruliad can be incredibly non-trivial.
Mm-hmm.
Very similar to the claim that's very similar to the claim that the continuum is kind of boring. But viewed from a Turing machine. Okay, so the from outside, the continuum is boring. From viewed on the inside by a Turing machine, it's elaborate, it's complicated.
Mm-hmm.
So in a sense, what this is saying is, this is a story of constructivism or something, or construction. I don't know whether it is constructivism, because I don't know what that is really.
Yeah, I think so.
Explain. Do you know, in other words, the fact that the thing you get, I don't understand this. Do you have a way to explain this?
Well,
I mean, in this case, we are just thinking of this in the simple sense that in order to build a theory, a statement, a model, whatever, you're constructing some proof trees that would be the derivation or the witness to that statement. All those constructions, when done from the inside, will only be in terms of the frames that the observer or the prover is able to build and observe and kind of detail from the inside. So in that sense, whatever lies beyond the computational capabilities of this observer will not be part of that theory.
but there's kind of a tragedy to it as well, which is that the TM has to construct something because it's on the inside. But being on the inside, it's computationally unbounded in a way that it doesn't actually get the full thing.
Absolutely.
So it needs to make the construction due to reasons that prevent the construction from actually being possible in full. Maybe that's why we do physics in the first place.
What do you mean?
Well, because we're TMs on the inside, right?
Yeah.
Right. So we're, in some ways, we're trying to construct our own bounded view.
That's correct. That's correct.
But we're also bounded as we're attempting to do it. But based on Stephen, one of the first remarks you made, we can still speak to the whole in some way.
Sure.
What's
the role of causal invariance in the whole thing?
Right.
I think the role of causal invariance is that there is a rulial relativity.
Well, you want to revisit this idea of the two slit for real?
I do, but I mean, but look, rulial relativity means the theory can have the same structure even though the basis is different. In other words, the aliens describing oh God, this is so weird. They can still have general relativity, but their degrees of freedom are completely different. So I'm saying the laws of physics, in the sense these meta laws of physics, are still the same, even though the coordinatization of the description of what's going on is different.
Mm-hmm.
Actually, the fact that the aliens still have general relativity is exactly consistent with what I'm claiming about multi-computation. Just as application areas for multi-computation still have GR, even though their interpretation is different. E.g., with, you know, interpreting space as monetary value. All right, so what we're saying here, but one thing about real relativity that's interesting is I think it's inevitable. I think in the ruliad, there's no escaping from causal invariance. Do you agree about that statement, that it's sort of obvious that there's causal invariance? I think it's a consequence of universal computation. Even confluences, you can always get back.
Yeah, right.
Mm-hmm.
I mean, even with the basic multi-computation that we've done, we've shown that there is confluence between rules. So why wouldn't it hold in real
Well,
space
there
in
can be
general?
confluence between rules, but there can be confluence. But this is saying when you've got everything there, there's no choice but to have a path back.
You have everything there.
Because you have all the possible rules.
All the rules in real space. You can't help but have a path back. Path back where?
Wherever you went in real space, whatever
Yes,
sequence of rules you used,
mm-hmm.
there's always another sequence of rules that can get you to the same place you got to. So in other words, if you branch somewhere and you've ended up in two different places, you can always get back together again. But I want to come to two different things. First, I think we should formulate the Lorentz transformation in branch Hill space.
Mm-hmm.
And I suspect it's related to these tensor networks and things. Second, I know Jonathan was talking about this idea of using negative signs and imaginary numbers, and what is this thing that was from the 19th century? Oh gosh, what's it called? The principle of, what the heck is it? The thing that tells you as you make a metric, or as you work with matrices, there are these different sort of, you can encode different directions in numbers. It seems like a hack. You know what I'm saying? That the concept of encoding, you know, first of all, you have negative numbers to encode time relative to space, or negative numbers for space, let's say, imaginary numbers for branch Hill space. Then what would you use for rule Hill space? The quaternions of rule Hill space. It's getting very ornate.
Are you sure we need to use that?
No, I don't think we need to use it. It's just a way of describing it numerically. So it's a way of getting something directly analogous to the Minkowski space. Okay. The thing that's interesting here is this idea that the universe operates according to definite laws is then put back to the concept of to have a coherent observer,
Mhm.
that observer can only pay attention to those things that make the universe appear to follow definite rules.
Sure.
And that if the observer went chasing after all these different rules, the observer would somehow not be coherent. Is that the right term? What's a good term that doesn't say conscious, but says that the observer has the attributes that that observer has is that they are representing a compressed it's a compressed and consistent in space, time, branchial space, rulial space.
Compressed and consistent evolution history in all these spaces.
Yes.
Right.
Yep. And that's saying that as you move around in space, you move around in space, you move through time, you have the same view of what's going on. So what's the analogy in space of not caring about things that you let's see.
What do you mean by not caring?
Well, I mean, the thing is, we're not claiming that the universe isn't having multiple branches of history, blah, 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 blah. It's just that we don't care about it.
Well, in ordinary space, looking outside the light cone, right?
Yeah, I see what you're saying. So basically, the observer sees only what is inside the light cone. The light cone.
And for quantum mechanics, it would be the cone that's in branchial space, but somehow it should include the branchial space and the physical space.
Oh, that's quantum gravity. You need that for quantum gravity. All right, let's make one more run at rulial quantum mechanics.
Can we discuss two-slit?
Yeah, we can. Also, I mean, with respect to these pictures and things, I think there's already non-trivial behavior at the level of the states graphs. I don't think you need to go to the causal graphs to discuss. I think it's already non-trivial. I mean, the final ruliad is trivial when, yeah, I mean, this is already non-trivial if you limit time. You see what I'm saying?
Yeah.
I mean, if we do this, right?
Saying the relations between
The
rules
states
is
graph,
non-trivial when we limit time.
yeah, are already trivial, already non-trivial. If we limit time.
Well, isn't that the entire lesson of computational complexity theory?
Yeah.
Yeah.
that's saying the front is those problems which are achievable in certain time. But in other words, as we approach the ruliad, as an entity within the ruliad, with bounded time, things are already non-trivial before we even go to causal graphs, I claim. Now, going to causal graphs, oh boy, I need to understand the token event graph version of this as well. But I'm pretty sure that it's right, that the key observation here is from within the ruliad is non-trivial. It is merely from outside the ruliad that it looks to just be, the infinity groupoid description is an outside the ruliad description. Does that make sense?
Yeah.
Yes, but there's no real observer to be bored in that way because it's just hypothetical.
Yeah.
Yeah.
But I mean, the fact is that as we add in rules, we're taking these different limits of adding in rules, adding in time. And your scheme for adding in rules by doing completions is a possible scheme, right, Xerxes?
Yeah.
As opposed to just purely sprinkling rules in there. But any of these ways of adding in rules, just like any of the ways of progressing the ruliad in time, is a foliation. It's a rulial foliation. It's a foliation across different states, essentially a branchial foliation, etc. So any of those things is just a different way to sample the construction of the ruliad.
Yeah. I suppose in the end, they should all be the same object. Whether you're sprinkling all the rules or you're just adding them hierarchically like I was doing.
Yeah, right, exactly. In the end, it's the same limiting object, but one's experience of it may be very different. And the question is, in the experience of it, what's the quotes right way to add rules?
That depends on what is it that you're trying to probe.
Well, okay, let's do the analogy. Okay, the analogy is, okay, so here's the analogy. The analogy is, how best to add rules in the development of the ruliad. Okay? That's analogous to what is the appropriate evaluation front, evaluation order in branchial, in the branchial space, I claim. So in other words, it's just like we can, e.g., so convenient that branchial is the name of some characteristic of a fish, because it means spell checkers don't flag it. Okay. So what we're saying here is this is the choice of how to add in rules is just like the choice of when to do which events. It is in fact just adding in which events, right? So in other words, it's like we have our standard evaluation order, and then we have exotic ones. You know what I'm saying? Like we have a standard Wolfram model evaluation order, and then we have more exotic ones.
Yeah.
Mhm.
So the question of adding in rules. Okay, so in the branch hill case, we keep on doing events, non-overlapping events, until there aren't more to do. Okay.
Okay.
And what's the analog of that? In this case, we keep on, I guess we do exactly the same thing. We could have the same evaluation front.
Mm.
For rules, if we wanted to. I mean, in the end, the whole thing revolves around how the observer chooses to parse the universe.
Yeah.
So we could add rules until if we have some way of understanding, okay, we're adding a rule, and now we've exceeded the span of the observer in rule space. Would that be helpful? That'd be helpful to know, right?
Yeah.
Yeah. How?
Well, I mean, it's an arbitrary thing. I mean, the extent of the observer in rule space is determined by the distance we've gone in inductive inference.
Right.
That which we do not know today. Okay, so as we do more experiments, we potentially shrink our profile, our size in real space. What does that remind you of? It's the uncertainty principle.
Good.
Mm-hmm.
So basically what this is telling us is that, my gosh, what is the analog of momentum in real space?
Mhm.
How does the uncertainty principle work? Let's see, we figured this out like a year and a half ago. As you go further in the multi-way graph, how does this work? There's some easy way to understand it. I think I wrote it down. As you go further, you get what I'm saying?
Wouldn't momentum be some flux through rule-like hypersurfaces?
It is. Yeah, surely is. Well, not.
But what does it mean?
Right.
What does it mean? I'm just thinking about.
Well, it's actually through time-like hypersurfaces. It's a flux. Energy.
Yeah.
Energy is a flux through rule-like hypersurfaces, and
But
which is to say, well, it's just the activity and the overall activity, but the issue is that I mean, there should be a deflection of the geodesics in rule space. What is a geodesic in rule space? Answer: it is somehow it's the way of getting from here to there.
Yeah.
It's the best set of rules for getting from here to there. It's the most direct description.
Yeah. It's the best form of compression, really.
Yeah.
Yeah.
All right, let's see. So we've got.
So wait, we could start to add rules, and we could maybe determine how much computational work it takes to translate from one rule to another. And then, but then we would know if we place different computational bounds on different hypothetical observers, we could start to have some sort of map of the extent that an observer could have in real space depending on how bounded they are, right?
Yeah. Yeah. Well, it's otherwise known as, do we understand the aliens?
Well, do we understand us? I mean, do we understand how computationally bounded we are? Do we know?
Yeah, well, it's a question. It's like whole brain simulation.
Emulation. Yeah. Yeah.
I mean, basically, look, one of the interesting cases of this is the fact that we can translate to each other's thoughts.
I know, it's already pretty remarkable, especially since we might have slightly different reference frames in real space, as we've an idea that we've entertained before.
That translation is already,
right,
in a sense, motion in real is yeah, I mean, continually trying to think about it from somebody else's point of view, thinking about things from someone else's point of view is continual translation, query, motion in real space. In other words, imagining yourself in a different, thinking about things from a different point of view, where point of view is now a conceptual point of view, not a physical point of view. All right, I have to switch to a cell phone in a moment. Well, not quite yet, but in a moment I can leave this Zoom session going, and then maybe James could take notes on whatever we figure out. We have another 15 minutes, and then I have to disappear. And James, are you around later?
Yeah.
But Xerxes is probably it's probably the end of Xerxes's wake cycle.
Yeah.
I think Xerxes is somewhat of a night owl, like me, but
yeah, but
like
Nick
is extreme. Nick is very extreme.
I'm not going to be available again until about 10:30 my time.
Okay.
4.5 hours from now.
Okay. Well.
Hold on. But we're not. We have a couple of minutes here.
No. I was yeah.
By the way, this point that real relativity is basically the statement that these laws apply in all these different systems. That's basically the point.
Mm-hmm.
All right, I'm trying to think. I mean, I will at some point try to write something coherent about the ruliad. And the question is, do I have really like to understand well, the uncertainty principle here. As we do more experiments, we shrink our size in Rulial space. What's the analog of that in mathematics? We don't quite know our axiom systems. Analog in mathematics
Well,
is the large cardinal axioms.
I'm still processing in my head whether the Gödel statement of consistency and completeness would be the analog of uncertainty, but I need to think of that a little more.
Right. But the claim here is, as we do more experiments, we shrink our size in Rulial space, is the statement, as we study more mathematical theorems, we decide if we need large cardinal axioms or not.
Mm-hmm.
Wow. Or couldn't it just be that we develop mathematical frameworks that translate between these in a more wieldy way?
No, because this is asking, we're shrinking our size in Rulial space is making the statement we are nailing down the rules for the universe.
Yes.
So similarly, we're trying to nail down the rules of mathematics.
Yes. Yes. So instead of it being scattered across a number of different fields where people can't communicate with each other well, find some way of, I'm thinking of like higher category theory, for instance. Wouldn't you say that we're shrinking our size in metamathematical space by finding a way to package that all together in, say, a single textbook?
It's an interesting claim. I actually think that's going the other way.
Well, I'm somewhat confused about what it means to shrink the size, because on the one hand, the translation speaks to breadth in Rulial space.
I know, but we're not talking about translation.
I know.
Can we nail the rules for the universe?
What does that mean to nail them?
It means that we have no more, we don't, the question, is there that additional weird particle that's, one electron volts and, 10 to the 50 electron volts in mass. Does that exist or not?
Oh, so by shrinking our size, it means that we're able to explain the continuum in a more rarefied way,
for example. But I mean, we're able to explain.
Okay.
We're able to explain what happens in the universe in a more complete way. We have much less uncertainty as we do more experiments. We have less uncertainty in the in every aspect of how the universe works. See what I'm saying? So I mean, in other words, and that's kind of obvious in a sense. I mean, in so
well, in some way, but the other point of view is that we're a Turing machine inside the continuum, and we're just performing more precise measurements, but not necessarily providing an understanding of how it works. Because what it actually is the continuum, but we don't have the computational resources to just know that kind of more plain fact.
No, but I think
so the earlier example about having everything in one textbook, it might not exactly be shrinking.
No, I think it's expanding.
What one is doing is abstraction.
I understand.
And when that abstraction applies, it's actually opening the domain to everything.
Yes, no, I agree. I retract that statement. I think it's more of it being expanded.
Right.
Yes, no, I'm confused about what it means to shrink.
Right. Abstraction is more about having a bigger bundle in Rulial space.
Yeah.
That the observer
expanding your reach in real space.
Yeah, well, the observer, right, can consider identical, can conflate, bigger region in real space that the observer can conflate. And I'm going to switch to a cell phone, and James could.
Yes, I have a notebook.
Okay, all right. I'll be right back with you guys. Hello.
Hello.
Hi. Okay, that's good. Hi. You guys there?
Yeah.
Still here.
Okay. Question: what should we be calling the observer? Do you think the term coherent observer is a reasonable meta description of the observer who maintains consistency in, in all these different forms of space? Is that a reasonable term? Is there some term, Xerxes, is there some term from the theory of consciousness that could be usefully used here?
Here, of course, you want to avoid any consciousness reference, but as such, what you're asking is, what should an observer have? An observer itself should be something or someone that is coherent.
Right.
So I don't know if coherent observer is a tautology, because if it's not coherent, what else is? Are they uncoherent observers or what?
Well, I mean, I'm coherent observer is an observer who maintains their, if you present them with the same thing, look, here's an incoherent observer. An incoherent observer is something that changes its mind about how to describe the number 3.
Okay, fine.
Every nanosecond.
In that case, you just need two things. You need coherence and persistence.
Oh, that's right. Persistence is a good other point. Yeah. That's a good other point. Which
coherence is too reminiscent of quantum coherence, I think. And consistency already has some other place in logic and in computation anyway. It'd be nice to just have some fresh word that's intuitive but doesn't draw any association with these other descriptions.
Oh, but coherent is not only in quantum. The coherent statement is used in a lot of other fields, including AI and other things like that.
What's the version in AI?
No, so for example, in cognition or in AI, coherence would just literally mean the colloquial sense in which we described it, that it is stable over some finite period of observation.
Well, which is basically exactly what we're talking about, which is
good. Exactly. Yeah.
Is there any consistent observer isn't the right thing, because that's not, it doesn't
yeah, so not consistent, but persistence and coherent, those are the two, at least those are the necessary conditions. We don't know if that is sufficient.
Yeah, I mean, I would claim that persistence and coherence are really the same thing. I mean, you can't be coherent across time unless you have some persistence.
But the persistence is for the structure of that observer or the model of the observer itself, whereas coherence is more with the function that persistent structure is performing.
Why does the observer itself, I mean,
don't you want the observer to be structurally persistent? Or are you imagining an observer that...
I assume they would be, but I mean, I think, I'm not sure I necessarily care, but yes, okay. Probably. I mean, in other words, the output from what does an observer do? An observer is somehow making a model. Okay, to be more specific about an observer, in tree traversal, for example, an observer is deciding which branches of the tree to visit next. That's a very low-level function of an observer.
Well, an observer is just a model builder, building models of the world around it in order to perform actions that ensures its survival or its persistence.
Right, but building models is in this case, building models consists of deciding in what is the sequence of
Exactly.
a tree traversal, right? So now the question is, what possible tree traversal orders are there that are not too wild? How do you enumerate tree traversal orders that are within the purview of a bounded observer? In other words, you need the analog of a Turing machine for observers.
Mm-hmm.
You need to be able to describe what kind of an observer is a reasonable observer. And in fact, can we actually use a Turing machine to be the observer? As in, right. So one possibility is that, yes, the question is, here's the obvious question.
Right.
Given the structure of the tree, is the ordering computable by some simple machine in some fast way?
Mm-hmm.
Right? In other words, does it take only bounded effort, given that you see the structure of the tree? So the question is, how does it do that computation? What it can do is it's locally on the tree,
Mm-hmm.
and it's moving around the tree. So it says go up, go down, and maybe the point is it homogeneous? As in, does it need a lot of information about the tree in order to do this? Yeah, that's really the criterion. The criterion is, can you make a tree automaton, so to speak, that's just wandering around the tree, trying to decide where to go next,
Mm-hmm.
and whose decisions are very straightforward. It's just like, don't go down a branch I've already gone down, go down the next branch next, et cetera, et cetera, et cetera.
Mm-hmm.
I think that's the issue. And if it needs an ornate, now the actual implementation of this in a measuring device is a different thing. I think we need to understand that a little better. But conceptually, it's a question of that's the criterion. That's what we have to have.
But
that's
the
what it means.
observer is not simply exploring some tree, right? The observer is also conflating different rules.
Oh, no, I know. For the rules, it's a much more complicated case.
Well, but it's not that much more. I mean, so you have some observer, you have different rules, you have a certain bounded computational resources, and you can, to whatever degree, you can perform the computational work to basically simulate these different trees so that you can translate between them, then you can include them within your reference frame, basically, right?
Yeah, but I mean, this question of valid formation, we do have a reason.
Stephen, you're breaking up. I can't
hello,
translate between your tree and my tree.
Hello.
Yeah, it's still a little weak.
Yeah, where it is that, to my knowledge, I'm only moving in my physical space location. Okay, question next, a few other questions. So I think there is a ruliad uncertainty principle. And the question then is, yes, here's the point. The place where the ruliad uncertainty principle becomes important is when there is an experiment that could go in different ways depending on which side of the inadequately inductively inferred rules you fall. You get what I'm saying?
Mm-hmm.
So in other words, that's the place where it matters down the rule that there could be different things that happen. Now, when there are different things that can happen, how do you detect that there are different things that can happen? Well, let's see. The thing that's weird, the thing that one would like to see is interference between different rules.
Did we discuss this once?
What's that?
We discussed this once, I think. It'll
Yeah.
be in some notebook from September. We discussed
Okay,
this with
well,
Nick
okay.
and with Xerxes, and
Okay, well, go look up the
right,
answer
you're
then.
not on the computer, right? Okay.
Yeah. So, okay, that's one thing. The next thing is rulial black holes.
Right. And this prevents translation to some degree.
Yes, it certainly does. I've got my thing and I'm sticking to it. You know, I described that in the original, that's right. I described this in the original description of the project. I talked about rulial reference frames being, I've got my story about how the universe works and I'm sticking to it. That's the initial frames.
Okay, so this is what you wrote about destructive interference on September 18th. Okay?
Yeah.
Okay, so you have two different proofs, right? But then we're going to look at them at some intermediate stage. This was the idea.
And then they're inconsistent. Yeah.
Right. So this is the idea.
Oh, that's nice. Yeah. Right. The two proofs are inconsistent at the intermediate stage. And so in physics, that would mean the two different descriptions of what's happening in the universe are inconsistent at the intermediate stage. They agree in what happens in the end, but at an intermediate stage, they're inconsistent.
That's right.
They disagree. So in other words, what one's saying is, my explanation of the universe is that there's an exchange of gravitons, and somebody else's explanation is, no, actually, it's an exchange of axions or something.
Mm-hmm.
And in the end, that produces the same force on the particle or whatever, but at the level of, because we didn't have enough, because let's see, we haven't nailed down, we haven't, I don't know. I think it's related to this.
It's like at that stage, it's like we can't, at that given moment, we don't have a program that simulates both of those back and forth at that exact stage. Maybe at the end, when we see the full thing, we can go back and forth, but we can't at that stage.
Yeah, right. At the intermediate stage, we can't readily get from one to the other. I mean, it might be possible, but it might be very far. It might be that okay, so in the kind of, you know, it might be the case that the things have separated a long way in rulial space. And okay, let's just go through the black holes in rulial space. So if there's an event horizon, that means that you can't get there from here. You can't translate between those two different things. They are incompatible views of the universe.
Well, you have reducibility at play as well.
Have which?
You have computational reducibility at play as well.
That's true. Well, you're saying that an event horizon is a place where there's an infinite path needed to get from one domain in rulial space to another. And a space-like singularity, which in this case is a rule-like singularity. The hell is a rule-like singularity? Let's just think about this. So what happens is time ends. Yes, from all rules, time ends. Wherever you come at it from, whichever rule you're using, you always come to the same conclusion. In other words, there's no longer the ability to see, from all rules.
So
Well, you
then
just-
there's
you
a
just don't-
branching horizon, rulial horizon.
It's like,
Yes, exactly.
I mean, it's just a.
There's a rulial horizon, but I mean,
But what does it-
presumably
what does it
there's a
mean, though?
rulial horizon if there's cosmic censorship in rulial space.
But what's the semantics of that? If it all arrives at the same point.
Well, the first point is that time has ended, so you can conclude no more.
So there.
It's
so
like,
there
and
isn't-
the answer is 42, and so what? It doesn't give you any opportunity to, I'm not sure, to reason further or something.
I see.
Um,
Oh, I see. Yes. So it doesn't
So
matter
you're-
what,
you're
it doesn't
stuck,
matter
you're
what you
finished.
learned because there's no
there's nothing more
there's
to
no
know.
post game to discuss it. Right. Yes, I see. I understand. Right. Interesting.
So that's the end of, that's some kind of end of knowledge. That's the place. Normally, knowledge is an endless frontier. And there are many different points of view that all go separately. This is a case where everything just converges to that state. Hold on one second here. Hi guys, I think I have to disappear in just a moment here. Are you still there?
Yes.
Yeah.
Yes.
Yes.
Yes. We haven't.
We are about to reach the
Yeah.
ultimate
the
real
singularity.
singularity.
Yeah.
Unfortunately, and
We're all knowledge ends.
well, actually, hold on a second. You know what? Hold on one second. Let me put you on hold for a second. Let me just try and transact this, and I'll be right back.
Okay. So Xerxes, maybe we could just quickly try and arrange something. So this week has been inordinately busy. I have some notes that I've been just wrapping up for the past few days, but I've just been too busy to actually finalize it.
Okay.
Hopefully, I should give you them tomorrow. So when are you available this week at all to meet and discuss?
Somewhere in the middle or the end, yeah.
How about on Thursday?
Say this again.
How about Thursday?
1 minute. Thursday.
Maybe that's neither the middle nor in the end.
No, Thursday might be okay. There'll be the colloquium. I'll
Yeah.
have one more student meeting on Thursday.
Mhm.
And I could try to fit in Thursday. I'll let you know then. Yeah, I think Thursday might be potentially possible.
Maybe we should just have a backup plan, because I think it would be good to meet this week, if possible. So if not,
Yeah,
if
Hi guys,
Oh.
I think this is hopeless and going to be too loud, so I think I have to disappear. James, I can call you later,
all
Okay.
right. Okay.
and
Right.
you might you should probably hang up on this Zoom session, otherwise we'll to be continued later.
Okay.
And
bye-bye.
Xerxes will tell you what happened.
Sure.
When you wake up tomorrow, there'll be a giant ruliad sitting waiting for you. Okay.
Okay.
All right. See you later.
All right.
Okay.
Bye-bye.
Bye.
Thanks, Stephen. Okay,
Bye.
Xerxes, we'll talk on the Slack.